All right, so we're going to start talking about basic arithmetic with matrices. So the first one we're going to start with is matrix addition and subtraction. What I'll do is I'll make sure in these videos that I'm putting some timestamps down below in the description so that you can figure out if you need to skip to a particular topic. You can look that up and do that. There won't be links that you can click on, but there will be at least guides as far as approximate times of when certain topics start. So if we're starting with matrix addition and subtraction first, so if I want to take a matrix A and I want to add to it a matrix B. So the long story short here is that they really just need to be the same size in order for us to do this. So if A has, m rows and n columns, so it's an m by n matrix, then really the only way to do addition or subtraction with another matrix is for that other matrix to also be the same size. In other words, it must have the same number of rows and the same number of columns. Okay, if we do that, then our sum, our matrix A plus B, this will also be m by n. Okay, and so the way we think about this is, since a vector addition is done entry-wise, right, when we've added just two vectors, here each entry in A is just added with the corresponding entry in B, and that will give us what the entry in the sum A plus B gives us. So I'm just going to write down some sample matrices here, and we'll do some examples. So if A is the matrix, we'll say the first row is 1, 2, 3, and the second row is 4, 5, 6. And let's go ahead and make a matrix B, and we'll call it something simple like 3, 6, 9, 12, 15, 18. You can see a pattern there, I think, right? I'm going to give you a second or a third matrix here. So let's say C is 5, 10, 15, 20, for example. So if we want to do, for example, A plus B, then we look at this matrix A. It has 2 rows, 3 columns. So this is a 2 by 3 matrix. And matrix B also has 2 rows and 3 columns, so it is also 2 by 3. So since they're the same size, the addition is defined. Okay, and so what we'll do is just entry-wise, we will add these together. So the 1 is in the first row, first entry spots. We'll add that with the first row, first entry in the B matrix. So 1 plus 3 there would give us 4. Here then the 2 is going to add to the 6. They are in the second column spot for the first row. So 2 plus 6 will give us 8. Of course, you can see what's happening here, right? 3 plus 9, those will add since they are corresponding entries. And then for the second row, of course, we add 4 and 12 will give us 16. 5 and 15 will give us 20. And 6 and 18 will give us 24. Okay, so our sum A plus B is defined. It is also a 2 by 3 because A and B were originally 2 by 3, and this is our sum. If we added these in the opposite order, did B plus A, I think you would probably see we would get the same thing. Instead of 1 plus 3, we would have 3 plus 1 for this first entry. 2 plus 6 would change to 6 plus 2, so we would still be able to do it if we swapped the order. So we could say addition is commutative, right? If we do A plus B, then that will equal B plus A in this case. Of course, if we try to do something like A plus C, then what we have is we have a 2 by 3. You'll notice C has 2 rows and only 2 columns. This is a 2 by 2. So C is 2 by 2. So A plus C, we don't have, I think, things for 3 and 6 to add to, right, when we try to do this. So the addition is not defined here. Okay, so addition is not defined. You might say there's no solution to this, possibly. But we cannot do the addition there. Okay, they're not the same size, so we can't do it. Similarly, C plus A would also, if we swapped the order, would not be defined as well. Okay, so that is pretty easy, I think. Let's go ahead and do something else that's pretty easy. We'll go ahead and do scalar multiple of a matrix. So for scalar multiple of a matrix, this is just like scalar multiplication for vectors. Okay, so it's done the exact same way as we did scalar multiplication with vectors. So if I have some real number, let's call it lowercase r maybe. So lowercase r, some real number times matrix A. So that's just a matrix whose entries are all basically r times the entries in the original matrix A, right? So if, let's go back to our, if A is 1, 2, 3, 4, 5, 6, then, let's say, -2 times matrix A, of course, we just multiply every entry by that real number -2, scaling it by a factor of -2. So we would get -2, -4, -6 for the first row. And then multiplying the second row by -2, we'd get -8, -10, -12. Okay, so it doesn't change the size, it just scales every entry in the original matrix A. If we go to our, what was our matrix C before? I think it was 5, 10, 15, 20. That was our matrix C before. So if we wanted to do something like 1/5 times matrix C, right? That's a scalar multiple, multiplying by 1/5. So of course, if we do that, we should just get what? 1, 2, 3, 4. Same size matrix. It's just everything is multiplied by 1/5 there. Okay, so those are pretty easy. Addition, subtraction, I think everybody can do subtraction. If you can do addition, you can do subtraction. You're just subtracting entries that are corresponding. So let's go on to, I think, something that needs a bit more attention, which is matrix multiplication. So we're going to define a way to multiply two matrices. We've multiplied, vectors by and matrices by a real number. We call that scalar multiplication. We've done things sort of like dot products and cross products. Those are ways of multiplying vectors, but let's look at multiplying matrices in particular. It's going to relate to a little bit of what we've already done before. So let's say I have a matrix A and its size is m by n. So it has m rows, n columns, and I want to multiply times some matrix B so that I get the product A times B. Okay, so the way we will do this is the method of computing matrix multiplication is we are going to perform dot products of the rows of A with the columns of B. Okay, dot product, which we've done before with vectors. So the way that we will need to do that, so in A, each row, so we have m rows, but each row has n entries in it. So to do a dot product, if there's n entries in each row here, we need n entries in the columns of B for that to work. Okay, and so the way that will work is this would need to be something like n by something else. Let's say n by p. I won't use O because O can tend to look like 0. So we'll say n by p. Okay, so the idea here is that this second dimension here and this first dimension here, okay? The number of columns in the first matrix needs to match the number of rows in the second matrix, and then we can do the dot product. Our product, as long as this is true, our product will then be m by p, and you might be able to see where we're getting that. Okay, let's do an example and sort of see what happens doing the dot product of the rows of the first times the columns of the second. So I'm going to write some new matrices A and B. So let's say A is 2, 1, 3, -1. And let's say that B is, let's make it a different size. So let's do 4, 0, 5, -2, 6, and -3. Try to keep these different so it's easier to see what's going on. Okay, so if I want to do A times B, so here's what we'll do. We're going to do the dot product of the, we'll just go in order systematically. I think that will be the easiest way to see this. Okay, so if we notice this is a 2 by 2, and here we have 2 rows, 3 columns, so this is a 2 by 3. So the important thing is that these match. So we know that the Multiplication is defined because those are the same. And we know that the sort of these outer numbers here, the rows of the first one, the columns of the second one, that will be the size of our answer. So AB, our product, is going to be 2 by 3. Looking at this here and this here. And so what we'll do is to create this, I'm actually going to just sort of write, so think about this will be 2 by 3. So we're going to have 2 rows and 3 columns. So you should be getting entries in a matrix that looks kind of like that. And what we'll do is we'll take, so for example, our dot product, we're going to take the first row of A, and if I do a dot product with the first column of B, sort of keeping the entries in order, these going left to right, these going top to bottom, when we do the dot product, because we're using the first row and we're using the first column, that dot product is going to go in our first row, first column spot, which will be there. Okay, so if we take our row 1 times our column 1 dot product wise, then that would be, we'd have 2 times 4 plus 1 times negative 2. So if we do that, first row times first column, then we'll get 8 minus 2, which is 6. So first row times first column goes in the first row, first column spot. Our 6 goes there. Okay, and we'll just keep using our first row until we exhaust all the columns, and then we'll move to the next row. So now we'll do first row times the second column. So this is row 1. This is column 2. So it would go in the row 1, column 2 spot, which will be there. Okay, so if we do that, then 2, 1 times 0, 6. So the 2 times the 0. So 2 times 0 plus 1 times 6. 0 plus 6 there gives us 6 as well. All right, so now if we do row 1 times column 3, so row 1 times column 3, that dot products is going to go in the row 1, column 3 spot, which would be here. And so let's go ahead and do that. So we would have 2 times 5 and then 1 times negative 3. That will give us 10 minus 3, which is 7. So I'll get 7 there. And now I've exhausted all the ways I can do a dot product with the first row and the columns of B. So now I move on to the second row. So second row, you can see, is going to fill in these spots, right? So second row, row 2, let's start back at the first column. So that will give us a dot product in the row 2, column 1 spot, which will be there. Okay, so if we do that, then we will have 3 times 4. I'll do it up here. 3 times 4 plus the negative 1 times the negative 2. So we'll get 12 plus 2. That'll give us 14 there. So 14 goes in the row 2, column 1 spot. Go ahead and take row 2 times column 2. So that will go in the row 2, column 2 spot, which is there. Doing our dot product there, we have 3 times 0 plus negative 1 times 6. And so that gives us 0 minus 6. That's negative 6. We're getting lots of 6's in there. And then last one here, right? This is row 2 times column 3 will give us the row 2, column 3 spot in our product. So here we'll do 3 times 5. Plus negative 1 times negative 3. So that is 15 plus 3, which is 18. So 18 goes there. Okay, so that's all of our combinations of doing rows times columns as far as a dot product goes. And we get our product here that is A times B. It's a 2 by 3 matrix, and those are the entries for that. Okay, let's do a couple of other examples. I guess one thing maybe that before I move on, I will point out here. Think about if we were going to do these in the opposite order, right? With real numbers, we can do something like, if I can do 5 times 9, I know that that's the same as 9 times 5. So with real numbers, we're used to the idea of commutativity, right? With multiplication, that I can swap the spot of those, do the same operation between those, and get the same thing. If we think about that with matrices, so think about b times a. So if I want to do b times a, well, b is a 2 by 3, and a is a 2 by 2. And what we'll notice here, the number of columns in the first one and the number of rows in the second one do not match. Okay, so this matrix multiplication is not defined. Okay, so you'll notice this is our answer for a times b. This is our answer, in other words, lack of an answer with b times a. So what you can see here, certainly if we multiply in different orders, we don't get the same like we do with real numbers. Okay, so matrix multiplication, we didn't even get an answer period when we tried to do b times a here. Okay, so matrix multiplication is not commutative. Okay, we cannot assume that we're going to get the same thing with a times b as we get with b times a. All right, let's move on. Let's do some more examples with this. So I'm going to write some new matrices. Let's say matrix A is, I'm going to do some square matrices. That's where we have the same number of rows and columns in a matrix. So here my A is -4, 1, -1, 0. Let's make matrix B into something like 0, 3, 2, 4. Okay, so with these square matrices, I think you might notice already we're actually going to be able to do A times B, and we'll be able to do B times A, because this is 2 by 2, this is 2 by 2, so it's not really going to matter when we switch them around, right? The number of rows and columns will always be 2. So let's do A times B first. Okay, so that is taking rows of matrix A times columns of matrix B. Now, of course, we should be getting a 2 by 2 here, right? So we should be getting 2 rows, 2 columns. Let's go ahead and do that. So first row times first column dot product is going to be -4 times 0 plus 1 times 2. That will give us 2. So 2 goes there. Next, I will do the row 1 times column 2. We'll put that in the row 1, column 2 spot. So that will be -4 times 3 plus 1 times 4. That'd be -12 plus 4 gives us -8 there. So this is -8. All right, so we have completed everything, you can tell by looking at the first row here. So now let's move on to the second row, dot products. So -1, 0 times the column 0, 2. So we would have -1 times 0 plus 0 times 2. That's going to give us 0. So 0 goes there. And then last, we would have a row 2 times column 2. That'll go in the row 2, column 2 spot. All right, and so we'll have -1 times 3 plus 0 times 4. That gives us -3. And so this is our product, A times B, 2, -8, 0, -3. Now, here we know that if we do B times A, of course, all of the, rows and columns are 2, so of course B times A is going to be okay to do as well. Let's again sort of see why we can't really trust, though, just to assume that because it's doable, right, because the multiplication is defined, that we necessarily get the same thing, right? So for B times A, we'll still have a 2 by 2 product there. So let's look at what happens. So with B times A, that will be the rows of column B, the rows of matrix B times the columns of matrix A. So my 0, 3 dot product with my -4, -1. So that gives us 0 times -4 plus 3 times negative 1, which is negative 3. You can already kind of see something different happened. We didn't get 2, so negative 3 goes here. Let's continue on, though. So now let's do the row 1 times the column 2 here. That'll go in the row 1, column 2 spot. So we will have 0 times 1 plus 3 times 0. Well, that's 0 there, so we get a 0 here. And that's all of the dot products with row 1, so let's do row 2 times the columns here in A. So 2, 4, dot product with negative 4, negative 1. So we'll have 2 times negative 4 plus 4 times negative 1. So we'll get negative 8 minus 4 there, negative 12. Negative 12 goes there. And then last, we have 2, 4, dot product with 1, 0. That'll go in the last spot there. So this will be 2 times 1 plus 4 times 0. That is 2 plus 0, which just gives us 2. So we get, you can see a different matrix. Some of the numbers are similar, right? But that's not necessarily going to be true. You can tell that we do have defined multiplication both ways, a times b and b times a, but they're certainly still not the same matrix, right? So again, another example of why you can't really say that we're going to get the same thing, not commutative. So make sure you remember that. Matrix multiplication is not commutative. That is an important difference between that and real numbers. Let's look at, it's not that it can't happen, it just most of the time it really doesn't happen. So let's look at an example maybe where it does happen. Just show that it's possible. It's just that most of the time it's not going to happen. So certainly don't want to count on it. Let's say we have a matrix A that is 1, 0, 0, 2 maybe, and a matrix B, let's go with something like 3, 0, 0, negative 1. Okay, so if we do matrix A times B here, so 2 by 2, 2 by 2, of course, it's going to be 2 by 2. I'm going to move a little more quickly through this, just we're seeing the point here. Okay, so 1, 0 times 3, 0 is going to give us 3. I'm going to skip the steps on this one. 1, 0 times this is going to give us 0. Second row, 0, 2 dot product with 3, 0 is also going to give us 0. 0, 2 dot product with 0, 1 is going to give us negative 2 here. Okay, so rows of A dot columns of B gives us this. If we do B times A, in this particular one, you'll notice that we get the same thing. Okay, so here, if I do the rows of B with the columns of A, so 3, 0 dot 1, 0, I would get a 3. 3, 0 dot 0, 2, I would get a 0. Moving on to the second row, 0, negative 1 dot 1, 0, we would get 0 there. And then 0, negative 1 dot 0, 2, we would get negative 2. So it is possible that you can get the same product doing it in either order. It just most of the time it doesn't happen. So it's not impossible, but just remember that most of the time those matrices will not commute when it comes to matrix multiplication.